A very good morning to all. This is P. Kavita, Assistant Professor from AAA Department at RMD Engineering College. Today we will see the efficiency derivation of a Rankine cycle. So first let's understand the basic working of Rankine cycle and then we'll derive the derivation for efficiency calculation. So the Rankine cycle comprises of four main components, which is the pump, where it is compressing the water and increasing the pressure of water, which is equivalent to the boiler pressure. Next, we have the boiler, which is operating at constant pressure to convert water into superheated steam by burning coal. And then the superheated steam enters into the turbine and it goes through isentropic expansion process where the thermal energy from the steam has been converted into kinetic energy, which rotates the turbine blades, and then mechanical energy which is produced from the turbine has been fed to the generators which is connected to it through the same shaft. So the generators will convert this mechanical energy into electrical output. The steam which is leaving the turbine will enter into the condenser and it will go through a phase shift or a phase change where the steam has been converted into liquid water again. The condensation process takes place in the condenser by allowing cold water to run in through the condensers. So it is also called as a heat removal or which is a heat rejection process. The condenser also operates at constant pressure and the steam which is converted into water has been fed to the pump again and the whole process keeps on repeating. So this is the Rankine cycle efficiency diagram which tells us the similar components of a Rankine cycle, and we marked all the work done by the components. In order to understand this very easily, we'll first see the equation for efficiency. Efficiency is equivalent to work done divided by the heat supplied. So what is the total work done in the above system? So the Rankine cycle system denotes the thermal power plant working or the steam power plant working, isn't it? So the total work done divided by heat supplied is the efficiency formula. So efficiency is equivalent to what is the net work done in the Rankine cycle? We have work done by the pump which is used to increase the water pressure, which is equivalent to the boiler pressure. And then there is one more work done over here, which is the work done by the turbine, where the heat energy or the thermal energy from the steam has been converted into kinetic energy, which rotates the turbine blades. And then the mechanical output produced from the turbine is fed to the generators to be converted into electrical output. So this is the work done by the turbine. So obviously from this entire system, we can understand that the work done by the turbine is very much greater than the work done by the pump. So work done by the turbine minus work done by the pump is the net work done by the Rankine cycle divided by the heat supplied. Heat has been supplied in the boiler, which is the burning of coal to convert water into superheated steam. And we also know that the turbine work done is going to be very much higher than the work done by the pump. So with the WP or the work done by the pump is a very small value compared to the work done by the turbine, it can be negligible also. Now we'll have to identify the values for WT, WP and Q1 and substitute it in the efficiency equation. So first, to begin with the boiler, so boiler work done is given by, let us check out what is the work done in the boiler. So the H value over here denotes the enthalpy, which is denoted by H. So what I've taken here is HF1. HF1 denotes the water which is entering into the pump. So since it is in fluid state, I've denoted it as HF1. And then the water leaving the pump is going to be of very high pressure and it is also going to be in a fluid state over here, which is denoted as HF2. And then the water which is entering into the boiler converts all the liquid water into superheated steam. So to convert it into superheated steam, there is some heat application or addition of heat energy over here, which is done by the burning of coals in the thermal power plants. And then what happens? This is H3. It is not denoted as a subscript of F because this is in a superheated steam state. It is not in the fluid state, so it is only denoted as H3, superheated steam. And then when it is given to the turbine, the steam which is coming out of the turbine is denoted as HF4, and then this HF4 steam will be converted into water again. So in order to understand the boiler work done, so HF2 is the input to the boiler and also Q1 is the input to the boiler. Is it clear? That is the way we'll have to understand it. HF2 is the water which is entering into the boiler, and also the heat supplied to the boiler is denoted as Q1. The output from the boiler is denoted as H3. So the equation of the boiler goes like Q1 plus HF2, which is equivalent to H3, which denotes the input equal to the output. Is it clear? So Q1 is the heat supplied to the boiler and HF2 is the high pressure water entering into the boiler. So these two combined together will produce a superheated steam, which is H3. So the work done by the boiler is Q1, which is the heat added, and HF2 is the high pressure water entering into the boiler, which is equivalent to the output of the boiler, which is superheated steam, H3. So from this equation, I want to get the value of Q1, which is equal to H3 minus HF2. And I'm taking this to be equivalent to equation number 2. So now let's understand the work done by the turbine. So what is the input to the turbine? H3 is the superheated steam which is entering into the turbine, and then the thermal energy from the superheated steam has been converted into kinetic energy, which creates a rotational force in the turbine blades, so which is denoted by Wt, and then the steam leaving the turbine is denoted as H4. So what is the input to the turbine? H3 is the input which is given to the turbine, and there are two outputs derived from the turbine. One is the Wt, which is the mechanical output taken from the turbine, and then H4 is the steam output from the turbine. So the equation will be as H3 input equal to Wt plus H4, which is the two outputs from the turbine. Is it clear? H3 equal to Wt plus H4, because the H3 is the superheated steam which is entering into the turbine, which creates the work done by the turbine, which is the mechanical rotation, and steam leaving the turbine was denoted as H4. So the equation is H3 equal to Wt plus H4, from which I require Wt to be equivalent to H3 minus H4, which goes to the other side, which is taken as equation number 3. Next is the work done by the pump. Let's understand it from the diagram. So water is entering into the pump, which is in fluid state, so which is denoted as HF1. Okay, along with this, there is a work done in the pump to increase the pressure of the water to be equivalent to the boiler pressure. So the pump is receiving two inputs. So HF1 is one input, and the work done to the pump in order to increase the water pressure is the second input, and it produces one output, which is HF2, which is the high pressured water. So the equation goes as HF1 plus Wp, which is equivalent to HF2. Input equal to output. So Wp plus HF1 is equal to HF2, from which I need Wp value. So Wp is equal to HF2 minus HF1, which is taken as equation number 4. On substituting the above equations 2, 3 and 4 in equation 1, we get efficiency is equal to, this denotes the work done by the turbine minus work done by the pump divided by the heat supplied. So these are all the values which we have derived from the above equations. And since we know that the work done by the pump is very negligible value, it can be omitted. So if the work done by the pump terminology is omitted, efficiency equation will be equivalent to H3 minus H4 divided by H3 minus HF2, which is the work done by the turbine divided by heat supplied to the boiler. So efficiency of the Rankine cycle is equivalent to H3 minus H4 divided by H3 minus HF2. Is it clear? Thank you.